Hi 242. In this video we are going to introduce section 13.5. Before we get to any theorems or any major findings, we're going to introduce an example and then that'll help us justify a theorem that we're going to state later. So I'm going to be working through an example. It's matched problem 1 on page 742. So if you would like to flip to that page in your textbook now, go ahead and pause the video, and it's going to be a continuation of example 1 on that page. So what we have here is we are given a daily cost function, and here is our cost function, okay, negative 7.5x squared plus 305x plus 625. And I've typed up the instructions here for us for this example, and in part A what they'd like us to do is graph the function and then calculate the change in cost from x equals 5 to 10, and then show that change on the graph itself. Okay, so let's go ahead and graph this thing first. I have my graphing calculator here ready. I have already actually entered in my y1 right here, I've entered in this cost function here, so I'm ready to graph it already. Okay, so let's hit graph. And you probably won't see that here if you just hit graph on yours. That's because I have changed my window so that I see the graph. I've changed it for x min and max 0 to 20 and y min max 0 to 4,000. Okay, so go ahead and make those changes so that you can see the graph also in your calculator, or just follow along with mine. Okay, so here's the graph of c of x. Notice on our paper here I've already produced a little sketch for us, right? There's c of x here. And now we want to calculate the change in the cost when I change production levels, right? When I go from 5 to 10, okay? So the change in the cost from doing one production level to the next, right? I have to calculate the difference between the costs at those levels, right? And so the change in cost is going to be represented by this difference right here, right? This, if I take the cost at 10 and I subtract away the cost at 5, that will give me the change in cost from going from 5 to 10, okay? And when I do that, when I write that expression there, I can figure out the values of the function at each of those places. Remember, by using my trace button on my calculator here, right? I can enter 10 into the value for x and hit enter, and it'll give me the value of the function when x is 10. And then I can enter 5 and also get the value of the function there, right? And that's how I got those two numbers right there. So their difference when we calculate that is 962.5 right here. Okay, and so I put dollars there because that is a change in cost, right? That's a change in dollar amount, okay? And when they ask us to show that on the graph, notice that this expression right here, this c of 10 minus c of 5, that's a difference in outputs, a difference in y values, right? Difference in cost. So because it's a difference in cost and y values here, that means that it's a vertical change, right? It's a difference between these two y values right here, yeah? So just calculating here the difference between those two things is finding the sort of the difference between these two y values right there, right? That distance right there, okay? That's what that right there represents, okay? So that handles part A, just doing that graph right there. For part B, we're asked to think about a new function. They ask us to graph the marginal cost function. Okay, well remember that word marginal? That word marginal means derivative, okay? And so if we want the derivative of the cost function, that's the marginal cost. Let's turn our page here. Okay, so for part B, I need to find c prime of x. That's the marginal cost function. Okay, and because c of x is just a polynomial, we can make use of all of our rules for the derivative. So it's negative 7.5 out front for the constant times the derivative of x squared, which is 2x, plus 305. This is the derivative of 305x, and the derivative of 625 is 0, so I don't write anything. Okay, so that means that we have c prime of x here, which is negative 15x plus 305, and that's our derivative. So in part B it says graph the marginal cost function. Okay, so in y equals, I've actually already stored in that derivative right there. I just need to go turn it on here so that you can now see it when I hit the graph button. And it doesn't look very good. The reason is because this cost function is way up here, really large values for y, and this marginal cost function is sort of down here with smaller values of the output here. So I've produced a little bit of a sketch here for you. I know that the y-intercept of this is 305 because this is a line, right? mx plus b. Y-intercept is 305, negative slope, so it sort of goes down like that. Okay, so that's the graph of c prime of x. And now it asks us to calculate the area between marginal cost function and the x-axis from x equals 5 to 10. Okay, well, if I use my sketch here, right, the area between the curve and the x-axis from x equals 5 to 10, that's all this stuff right here, yeah? All that stuff, okay? And this is now, if you can recognize this is starting to tie in with what we've been doing in chapter 13 so far, right? Area underneath a curve. This should sound a little bit familiar. We did it with rectangles, but then we decided that was too complicated, so we decided to use a limiting process and turn it into a definite integral. Maybe we'll write that in a little bit, but for right now, let's just see if we can do this using some geometry, right? So if we want to calculate the area between marginal cost and the x-axis, what that means here is I need to interpret this in terms of a shape that I might recognize, right? Well, this is a trapezoid, right? And we have a formula for calculating areas of trapezoids. Here it is, 1/2 height times a plus b. And if you can't remember what all these little letters mean, right? Height is just the distance here, right? This is h, and then a and b are going to be the lengths of these parallel sides here. So we'll just call this a and we'll call this b. Okay, great. So if I go ahead and plug in these numbers now, right, I'm going to get 1/2. What is the height? Height is, let's see, it goes from 5 to 10. So h is 5. And then I need to do a plus b. Okay, well, I need to know what a is. What is that length right there? Well, that's what the value of the function, the length of that is going to be what the output of the function when the input is 5. Okay, well, we can figure that out. We've got a graph of the function right here. So let's trace and make sure we're on y2, so we're on the line down here. When the input is 5, enter, what do I get? 230. Okay, so you know what, let's start a new line down here. Let's put this on a new line so we have plenty of space. So this is 1/2, we said h is 5, times 230 is a, plus, what is b? Well, b is what? The output of the function, or the height right here, when the input is 10, yeah? So, okay, let's see what it is when it's 10. Let's see, 10, let's enter 10. 155, 155. Okay, so let's see, doing a little bit of number crunching here. If I go out here, let's see, 1/2 times 5 is 2.5 times, let's see, 230 plus 155. Hey, that number looks familiar. 962.5. Where have we seen that number before? Where have we seen that number before? Let's go back a page. Hey, that's the same number. So in part C, when it asks us to compare the results from parts A and B, they're the same. Those two things are the same. That's interesting. Well, notice that I said this sort of reminds us of something that we did in 13.4 with that definite integral, right? Can I write that area right there as a definite integral? Can I do that? Let's see. So let's see. Let's pick a different color. How about blue? So this area that we just found, I could have written it as a definite integral from 5 to 10. And what was the function we found the area underneath? It was c prime of x, right? Interesting. Okay, and what we found between parts A and B is that these two calculations here, calculating the difference here, the change in cost going from 5 to 10, and calculating the area underneath the marginal cost function from 5 to 10, those are the same number, right? So what that means is that I can take this expression here, this c of 10 minus c of 5, which is 962.5, and that's the same number as this definite integral, right? Because that's the area underneath the curve, right? That's 962.5. So our finding here, if we wanted to summarize, is that this c of 10 minus c of 5 is equal to integral 5 to 10 c prime of x dx. And that's really important, right? Both of these two things are both equal to 962.5, okay? And that's a really important finding. What we're finding here is a relationship between, notice, this is a relationship between the c function and the c prime function, right? It's saying if you do something with c prime over here, you're going to get something in terms of c, right? It's going to be a number, right? Area under this curve, change in the cost function, and those two things are equal. But this is sort of the precursor or example, or I guess justification for what's called the fundamental theorem of calculus, right? And this is really important, obviously, because it's called the fundamental theorem. Theorem, I always think about when I say this, I should make it sound, you know, sort of more impressive, like the fundamental theorem of calculus, or so dramatic like that, or something like that. Anyway, so if you'd like to see a theorem or a box for it, this is on page 743 in your textbook, right? But what's important here is that we sort of look at some notation here, right? So let's say we have a function f that's continuous. If we know that capital F is an antiderivative of little f, and that's the standard notation we've had for an antiderivative so far, so that shouldn't bother us so far, then what we know is, let's go back a second, let's see, how are c prime and c related? Isn't c the antiderivative of c prime? Yes, c is the antiderivative of c prime. Okay, so if we have f is the antiderivative of little f, then that means I can say that if I have something like this, if I have f and I want to go from a to b, right? That's kind of like my c prime right there, right? That's kind of like c prime. So if I write this here as c prime of x, then what does that mean? That means that I'm able to write c of b minus c of a, right? And go back a line, go back a page, right? If I have the integral c prime from 5 to 10, then that's c of 10 minus c of 5. Those two things are the same. Okay, so if I go from a to b, this is c of b minus c of a, or more specifically with our f notation here, where capital F is an antiderivative of little f. So if we have this area underneath a curve right here, this area under f from a to b, we can find that by doing what? Knowing an antiderivative of little f, which is capital F, and evaluating it b and a and finding the difference. Okay, so this is now a tool by which we can calculate definite integrals, but notice we use antiderivatives to do so. Okay, we'll talk definitely more about this theorem, but at least for right now, that's an introduction, an example justifying this theorem, and then in our next video for Friday, we will talk more about this theorem.